Okay, hello everybody, and welcome to our Digital Scholar webinar series. This one is it's hosted by the Southern California Clinical and Translational Science Institute at the University of Southern California. My name is Eric Peterson. I am an associate professor in the Psychiatry and Behavioral Sciences Department in the Keck School of Medicine at USC. And just so you know, we do these every month, so please keep an eye out for the next ones that we're going to be doing. Today, we're going to have an opportunity for question and answer periods. So if you're familiar with Zoom, you can go down to the Q&A or even the chat feature and type in questions as they come up. I will help facilitate the question and answer period, and we'll do those at the end of the talk today. So we're really excited to host Dr. Marcus Konkol today.
Great. So hello everyone, and nice to meet you. My name is Marcus Konkol. I am the Open Science Officer at ITC, which is the Geoinformation faculty at the University of Twente in the Netherlands. The position of an Open Science Officer is not very common, I would say. So I interpret the position as some sort of a consulting position. So more than 1 year ago, ITC decided that they need to do a bit more in the area of open science, which is why they decided to allocate a position for that. My job is basically to help ITC make the transition towards open science. I try to raise awareness for open science, for example, by giving presentations, as I do it right now, but I also help individual researchers to adhere to open science requirements, for example, when publishing papers, when writing grant proposals, and stuff like that. Before I came to ITC, I worked on a research project called Opening Reproducible Research, in short O2R. In this project, we worked on a reproducibility infrastructure, but I will talk a bit about more. I will talk more about that later. So now at ITC, I'm also working on a reproducibility infrastructure that assists researchers in overcoming the barriers to publish open reproducible research. And this brings me to the agenda and the learning objectives of today's talk. As I said, I am working on a reproducibility infrastructure that assists researchers in overcoming the barriers to publish open reproducible research. If you wonder what a reproducibility infrastructure is in this context and what the barriers are and what open reproducible research actually means, you don't need to worry because this is what this presentation is about. So let's start with discussing the term open reproducible research. Reproducible research, first of all, refers to achieving exactly the same results, for example, tables, figures, and numbers, as reported in the paper, by using the same source code and data. In open reproducible research, these materials are publicly accessible. Replicable research refers to coming to similar conclusions based on newly collected data or a newly implemented analysis. Open reproducible research and replicable research are often used interchangeably, but it is important to know the difference. Some would say that replicable research is a bit more important than reproducible research. In my opinion, this is a bit of a pointless discussion because both concepts are essential for scientific work. Let's assume you would like to replicate a study and you don't achieve consistent results. What can you do? The first thing you can do is to investigate the data and the code of the original study and check whether there are any issues or differences to your analysis. In this talk, we will stick to reproducibility as it is defined here. The Turing Way project provides a nice overview of existing terms and what they mean. Here you can also see that reproducibility means using the same data and code. Replicability means using the same analysis but different data, which is slightly different to the previous definition. In the previous definition, I said that replicability means using different data or a different analysis. So there's still some confusion out there. However, this is not a big problem. So if you're talking about one of these terms, just make clear from the beginning what you mean. For the sake of completeness, robust means using the same data and a different analysis, and generalizability means using a different data set and a different analysis. As I said, however, in this talk, we will focus on reproducibility. So, same data, same code. That sounds pretty clear, doesn't it? It actually sounds a bit like reproducibility is the easiest of the four concepts. You just need to use the same data, the same code, run it, and then you are done. But is it really that easy? In 2016, Monia Baker published a paper in Nature about reproducibility. She asked more than 1,500 researchers if there is a reproducibility crisis. 38% said, yes, there is a slight crisis. 52% even said, yes, there is a significant crisis. So in total, 90% think it is impossible to achieve the same results by using the same code and data, which is quite an alarming number. Well, you could say, yeah, come on, this is just a wrong or exaggerated perception. It's not that bad. But is this really the case? In this paper, the authors found at least one inconsistency in half of the articles. You could say, yeah, well, the papers were maybe rather old. Now it's better these days. But is this really the case? This paper is from 2021. Only 9 out of 25 papers were reproducible. 16 showed at least one major numerical discrepancy. You could say, yeah, well, maybe this is just an issue in psychology. But is this really the case? I also did a study in the geosciences. Same here. Only 2 out of 41 papers were executable. The remaining papers were either not executable or produced different results. Apparently, reproducibility is not specific to a certain discipline. It's a problem in chemistry, in biology, in physics, in medicine, in the earth sciences, and probably in every discipline that relies on data and code. Many researchers failed already to reproduce an experiment. But why is unreproducible research actually a problem? Well, we are not re-executing the code just for fun. There's a reason behind it. First of all, providing access to the analysis can help authors and reviewers find errors in the analysis. This is not possible if you just provide a textual description of the algorithm in the paper. Even pseudocode is actually not enough, since what you implemented might still be different. However, I have to admit that accessible code does not mean that you can also find the errors. Code can be very complex, and investigating it in detail takes a lot of time that reviewers cannot invest. So they are already overloaded with work. We cannot expect that every reviewer is checking the code line by line. However, if the code is there, you at least provide the opportunity to find errors. So if there are reviewers who are very good at programming, who have a lot of experience, who don't need much time to find errors, then they can look at that. This brings me to the second point. Reviewers cannot verify the results if the materials are not there. All they can do is to trust what is reported in the paper. And how about alternative parameter settings? If reviewers want to know more about it, it takes quite some extra effort for authors and eventually also for reviewers. So the authors need to rerun the analysis using a different set of parameters. They need to report on it, they need to resubmit the paper, and reviewers need to reread the paper, and so on. As I mentioned before, you can try to describe your analysis in pure text, but this is pretty difficult. So it's pretty difficult to understand it without the actual implementation. So at the end, the analysis might not be fully understandable. This is a problem during peer review, but also for those who would like to build up on the work. And this brings me to the final issue. Not reproducible work is also not reusable. Other researchers, for example, PhD candidates who continue the work of previous PhD candidates or students or postdocs, whatever, they need to start from scratch if they don't have access to the materials, particularly if it's not reproducible. And this, of course, takes time and money at the end. So this way of practicing research is not sustainable. All these problems are actually known. You could say, well, yeah, maybe this is just a problem of only a few researchers dealing with code. But once again, is this really the case? In fact, it's impossible to conduct research without software, say 7 out of 10 UK researchers. 92% of academics use research software. 69% say their research would not be practical without it. 56% say they develop their own software. 56 is the smallest number of the three. But imagine that every second researcher produces his own software. To me, it sounds like this is quite a lot. So reproducibility is an issue for many, many researchers. And there are actually quite a few selfish incentives to make your code reproducible. First of all, reproducibility can help to avoid disaster. As I said, if the code is not reproducible, it is difficult to find errors. If you cannot find errors, you might publish findings that are simply wrong. And this can have several severe implications. In medicine, it can mean that patients receive the wrong dose of a drug. In my area, in the geosciences, it's usually not that life-threatening, I have to admit. But however, I'm thinking of climate change. There are currently many decisions being made to address climate change, many political decisions. And many of these decisions, well, at least some of these decisions, are based on scientific findings. If the findings are wrong, the decisions might be as well. What makes it even worse is the current tendency in society to deny scientific findings. So publishing flawed science makes it even worse. Reason number 2 is that reproducibility makes it easier to write papers. It might happen that you need to change parameter settings. So remember the reviewer example, who wants to know more about different parameter settings. Maybe you have to try out another data set and stuff like that. So this is, of course, much easier if the code is reproducible. I mentioned the third reason already. Reviewers might have a number of questions regarding parameter settings. If they can access the code, they can look them up by themselves, which saves time for everyone. The fourth reason refers to the continuity of your work. It's usually not the case that you write a paper and start something completely different. For example, in a cumulative PhD dissertation, the papers build on top of each other. So continuing the research is also easier if the code is already reproducible. Finally, reproducibility will certainly help you build your reputation. You are transparent, you have nothing to hide, you give others the chance to verify your work, to build up on your results. That sounds pretty cool. Still, so much work is not reproducible, as we have seen on the previous slide. Why is that? And this is where you come to play. So I would like to know from you why you think that so much work is not reproducible. I kindly ask you to go to menti.com. Menti.com is an online survey tool. And if you enter the code 5444079, you will get a text box. And in this text box, I would like you to give a suggestion why you think that so much code is not reproducible. I will give you a few seconds. So this is what we've got so far. One person is saying it takes too much time on the researcher's part. This is certainly not wrong, and I hear that quite often. Another point is funders don't support it. In the Netherlands, we sometimes have these initiatives where you can apply for funding to make your code and data available. Researchers move on to something new. This is also what I hear from time to time. So if you publish the paper, then it's basically done, and you don't want to spend more time on making something reproducible that is already there. So this is also something that I hear from time to time. All right, let's continue. There are several more reasons for that. So first of all, methods and data sets are often not available. So it's a fundamental requirement is missing. Another issue is insufficient peer review. So many peer reviewers only check the article and not the code in the supplements, because they are already overloaded with work, as I mentioned before, and it takes too much time. Many researchers also lack the skills to publish reproducible research. For this reason, teaching is one of the most important means to solve this issue. Ideally, it starts already on the student level. There's a framework for that, so the framework for open and reproducible training that can help to create teaching materials based on reproducibility. However, these skills are important at all stages of the research career, including early career researchers, senior researchers, and also department heads. So it's important that institutes and universities create an environment that endorses, that fosters, and also encourages open science practices in general, but also open reproducible research in particular. But there are more reasons for why so much work is not reproducible, and these reasons are closer to what we've seen in the responses. First of all, many researchers fear losing their competitive advantage. So what if others publish papers faster based on the materials that you made available? We could also solve this issue maybe by publishing the materials at the very end of the research process. But then we come to the third response that we got. So if research is done, then researchers usually start with something new. Another possibility to solve this issue is to impose an embargo on the materials for 1 year or so. So you go to a repository, you deposit your data on this repository, you put an embargo on the data, and then you don't have to do anything else. So you can just say, well, you can publish the data in 1 year, and as soon as the embargo expires, the data will be published. Another problem is that preparing code and data takes a lot of time. But is this really the case? So it might also save you time, since it happens quite often that you need to redo the analysis. Anyway, even if it takes time and you don't want to invest time in code preparation, you could just provide a bit of documentation. And better provide the code as it is than not at all. Some researchers say that the code is only working for a very specific use case and thus not worth publishing. But you never know, it can be gold for someone else. Another issue is proprietary software, particularly point-and-click software. And this can only be solved by using open source software, ideally scripting languages like R and Python. Some researchers say that they are missing supporting tools. We will see later how this can be solved. Licensing is also not easy and not an easy topic, so it's difficult to understand. But many universities usually provide support staff for it. For example, data stewards or research data managers, or even open science officers. So the way I presented these reasons for not reproducible work, it sounds a bit like it's the researcher's fault, but it's not. I don't want to blame researchers. I can even understand some of the concerns. So the main problem is that they are part of a system that strongly relies on 3 very problematic pillars. If researchers get evaluated, for example, when applying for a job, promotion, or tenure, then there's a strong focus on how many papers you have published. Also, in which journals you have published them, and how many citations you have collected so far. Those who make these decisions rarely take into account how transparent a researcher has worked so far. For example, how often the researcher made the materials available. So it is not very surprising that many researchers think that reproducibility was not yet relevant for them. Why investing effort in something nobody is asking for? However, this will change. Let me tell you why and how. There are more and more initiatives that have open science on the agenda. The UNESCO, so the United Nations Organization for Education, Science and Culture, released a recommendation draft on open science that requires publicly accessible materials. The European Open Science Cloud is the largest endeavor in Europe to create an infrastructure for sharing materials. The largest funding program in Europe, Horizon 2020, also provides guidelines for open access to papers and data. These 3 initiatives are rather top-down, but there's also an increasing number of bottom-up initiatives. For example, reviewers start rejecting articles that do not provide access to the underlying materials. How can they evaluate a paper if they cannot fully understand it? In the Netherlands, some researchers interested in open science teamed up to create so-called open science communities. These communities create a space to discuss topics around open science, including open reproducible research. They also inform about open science practices and share concerns. These communities are open to everyone, so no expertise is needed, just curiosity. I am co-organizing the open science community in Twente. And if you want to organize your own community, don't hesitate to do that. So feel free to check out the starter kit that is linked below the map and just start. So if you need advice or something like that, don't hesitate to contact me. I'm happy to help you to create your own open science community. So it's all about accessibility, but is this actually enough? As I mentioned before, I also conducted a reproducibility study. I searched for articles that had code and data attached. This is actually already great, and it is not very common. But I wanted to see if providing access to code and data is actually enough to get the same results as reported in the paper. So I downloaded the code, I downloaded the data that was attached to the paper, I executed the code and compared the produced figures with those from the original paper. What you can see here is one example. On the left, you can see a screenshot of the original map from the paper. On the right, you can see a map that I got when I ran the code. I highlighted some of the differences. For example, the reproduced map does not have national borders. This is what you can see in this orange square, for example. The national borders are missing compared to here. The scale bar on the right, the scale bar is on the right and it is not below the map. Such differences are rather design-related differences. You could say, well, design is not that important. I mostly agree with that, although I have to say that if the design is different, it's difficult to compare two figures. However, the reproduced scale has 5 classes, whereas the original scale has 7. The reproduced map also shows points that do not exist in the original map. So if you are looking at the green square, you see 2 dots, and these 2 dots are not available in the original map. So the actual numbers are also different. And this is where it is getting serious. Why is that? I kindly ask you once again to go to menti.com and answer that question. Maybe you have an idea why the 2 maps are not identical. So what has happened? Just remember, the article was already published. There was a link in the article to the code and the data. I downloaded the materials, I executed them, but I got a different figure. So what do you think has happened? Do you have an idea? So we have already 2 responses. One person is saying, not all data was made available to me. This could be a good reason. Perhaps the researchers were selective in what they reported. This is also a good point. So there is this questionable research practice of selective reporting. But yeah, this could be also true. I made a mistake. This is certainly true. This can happen. But I just took the code as it is. I ran the code, and this is what I got. Unfortunately, we don't know the reason for that. We don't know why the 2 maps were different. I contacted the authors of the paper and they were also surprised, and I believed them. We can only speculate what has happened. Maybe they were playing around with the parameter settings and lost track at some point. Maybe they changed the code after they inserted the figure in the paper and then forgot to update the figure in the paper. Maybe the code was work in progress. It could be that they changed the code after they published the paper. Most of these issues are not intentional, but some of them might emerge due to the very complex nature of computational research. So maybe the reason is somewhere else. We should focus not solely on the source code, but also on the computational environment. To get a feeling what the computational environment entails, let's check the following example. So I try it out by yourself, but of course, you will get the slides afterwards, and then you can follow the 2 links and try these examples out. So here we have 2 Jupyter notebooks that apparently produce different maps. So we have a similar situation as we have in the previous slide. Just by reading the code, what could be the reason for why they produce different maps. This question is a bit mean, because if you look at the code carefully, you will notice that the two codes are identical. The difference that creates the difference in the map is more something like under the hood. Let's take a look at the dependencies of these Jupyter notebooks. For the left Jupyter notebook, we have a list of dependencies, and we have a very similar list of dependencies for the right Jupyter notebook. The only difference is the version of the matplotlib library. On the left, it's 1.53. On the right, it's 2.0. Apparently, these very small differences produce very significant changes in the output. So the maps look completely different. Making code and data available is apparently not enough. The versions of the libraries are also essential to achieve reproducibility. I don't know whether this explains the differences in the maps we have seen on the previous slides, because usually information on the computational environment, including library versions, is usually missing. And this brings me to the final chapter of this talk. Infrastructure for publishing reproducible computational research. Last year, we did a little survey of 11 existing infrastructures that help researchers make the computational workflows available in an executable and reproducible way. So it is not only about making code and data available, but also about being able to run the analysis and obtain the same results. This goes a bit in the direction of one-click reproducibility, which is something like the ultimate desired state of reproducibility. To achieve fully reproducible results, all the applications more or less rely on the concept of a research compendium. The idea behind the research compendium is to create a package that includes all materials necessary to reproduce the results. The materials include the text, so the paper itself, the data sets, and the code. These three components can be combined in a notebook, which is based on the concept of literate programming. Two famous examples, one we've seen already, the Jupyter notebook for Python and R Markdown for the programming language R. For those who haven't worked with notebooks yet, this is how they look like. So on the left, we have the Jupyter notebook that we've seen already in a Jupyter Lab environment. Jupyter Lab is basically an interactive development environment for coding, writing nodes, including graphics, stuff like that. And you can also run it in Python, R, Julia, and many others. On the right, we have an R Markdown file in RStudio, which is basically the same stuff, but for R. But we have learned that it is not only about these three components, it's also about the computational environment. If the computational environment is not considered, we cannot guarantee that others can reproduce the same results or execute the code at all. And this raises the very obvious question, which of the applications that we surveyed do consider the computational environment? Fortunately, most applications do it more or less. So I'm not entirely sure about the three on the left. So Authorea, Galaxy, and Manuscript. Many things happen under the hood, and I can't say for sure that they do not consider the computational environment. But at least I couldn't find information in the documentation. And how about literate programming? Most applications fortunately support at least one literate programming format. This does not mean that with some configuration you can also use R Markdown, for example, in an application that only supports Jupyter Notebook. But if you look at the documentation of applications, these are usually the formats that are supported by default. In the best case, an application supports both R Markdown and Jupyter Notebook. As I said at the beginning, I worked in the project O2R, and we only supported R Markdown. So why haven't we done that also for Jupyter notebooks, you might ask? Our goal at the beginning was not to have a fully operational platform. We were more of a research project and we wanted to try things out. We were also a small team. So we decided to do one thing well instead of two things halfway. But if you want to reach many people, you need to go for both. Let's take a look at another example, so Binder. Binder makes it very easy to create reproducible workflows. If you have a repository, for example, a GitHub repository with Jupyter notebooks or our Markdown files, all you need to do is creating a configuration file that specifies the version of the libraries you are using in the code. Then you can simply paste the URL from GitHub, GitLab, or Zenodo and create the required environment. In this example, we have an analysis, including an R Markdown file and some data sets. And with one click, we can create an RStudio session and rerun the analysis. This is how an eLife paper looks like. So an interactive paper published by eLife. On the left corner, we have a button to run the entire document. So it's one-click reproducible. We can change the code within the document and rerun the code, for example, based on new parameter settings. And we can also change parameters below a figure and then see how these changes affect the output. This is pretty impressive, but as you can imagine, this takes quite some time. So creating these interactive papers takes quite some time, effort, and stuff. So it is a bit questionable if this approach is scalable to a very large number of publications. However, you can also create such a document by yourself. So the tools to create these interactive papers are completely open source and available to everyone, which is very nice. CodeOcean is a different example. So they provide the code and the data below an article as a supplement. Readers can explore the code in a separate window. But if you want to do more, you have to sign up. So the three examples are very different. The binder service itself is for free and not connected to a publisher. You could do that if you are running your own journal. eLife is a publisher and hosts the service, but software is open source. And CodeOcean is a commercial company that provides the infrastructure as a paid service. The question is, what do publishers want? Do they want to rely on an external free service? Do they want to host their own service and tailor it to their needs? Or do they want to pay money? Publishers usually refrain from hosting data. So most of them ask you to store the materials somewhere else. This raises the question of whether the applications allow free self-hosting by the publisher or if they are provided as a service. There are three applications that are not released under an open license, do not allow self-hosting, and are provided as a service. These are the applications on the left: Authorea, CodeOcean, and Giganto. It is not surprising that these three applications are the only commercial ones. It is also not surprising that the non-commercial projects are grant-based, so they receive funding. Why is that important? Some of these services, like Binder, provide free online versions. The online versions do not have unlimited resources, but you can do already quite a lot with them. Publishers might be tempted to say, oh, great, yeah, our authors should use these provided online services. They are for free, awesome, reproducibility is great, let's go for that. But grant-based projects expire at some point, and the services will be offline. This, of course, has huge implications when it comes to sustainability and long-term availability of reproducible materials. Let's continue with the authors. What are the authors interested in? The authors might also be interested in knowing when to use what. I try to map the applications on the research cycle. So in short, the researcher usually starts developing the idea, then they design the study, collect data, analyze it, write a paper, and submit it for peer review. If the paper gets accepted, it will be published and can be used by other researchers. So the mapping is a bit of a suggestion and some kind of an estimation. So people who used one of these applications might have a different opinion, but it's just for trying it out. There are applications that provide a coding environment. So you can use some of the tools when you start analyzing the data. This is not the case, for example, in Reproducible. Reproducible actually takes the materials, so the code and the data, creates a reproducible package, and this is what you can send around. So this using Reproducible makes more sense to use if the analysis, after the analysis is done. Of course, it might make sense to use it in between to check if the analysis is reproducible. Manuscript and authorea focus more on the writing part. So they provide an editor to write text. There you can also include figures. You can add code to these figures. But again, this makes more sense if the analysis is already done. The next one is O2R. O2R focuses on an even later stage of the research process. At this stage, the analysis is done, the text is written, and now it's all about making it executable and reproducible for peer reviewers, and afterwards also for readers. Finally, eLife, we have seen it already. eLife takes action after the paper is accepted. eLife is a team that helps researchers create reproducible and interactive papers. And yeah, so as you can see, it might be worth considering to use different tools at different stages of the workflows. So the tools do not necessarily compete, but complement each other quite well. The research cycle is also pretty well reflected in the workflow that describes how the whole tail application works. It starts after the data is collected. The data is stored in an external repository. Researchers then start our project and also need to specify the computational environment, including the R version, the version of the libraries, and so on. After the metadata is added to the project, the researchers can upload the R files. But of course, you could also create R files within this environment. In this environment, the code can be made executable and then also published again in an external repository. So the whole tail platform can then be used by readers to execute the code. Speaking about readers, what are they actually interested in? First of all, they need a way to find papers. Once they've found an interesting paper, they need to be able to inspect the materials. They might also be interested in manipulating certain parameters, as it is possible with eLife papers, and see how these changes affect the final output. Finally, they might want to substitute the dataset by an own dataset and see how the results change. All these needs affect the reviewer's understanding of the paper. Ideally, each step contributes to the understanding of the reader. Comparison is more of a cross-cutting task that is important in each of these steps. So we also checked in our review whether the applications support these needs. Many applications support many of these features. So execution is the most common feature, not very surprising, but manipulation and inspection is also supported. However, not all applications provide a search functionality, and substitution is very uncommon, mostly due to interoperability issues. So imagine you have two different data sets, just simple tables, and if the column names don't fit each other, then it's also already not working. So this already creates interoperability issues. And I'm not even speaking about data formats. In our O2R project, we also focused on these needs and implemented them in the following way. So on the landing page of a paper, readers can read the paper and at the same time check the analysis and the data. They can also re-execute the code to see if the results are reproducible. And afterwards, they can also manipulate individual parameters, for example, using a slider. To make the changes after a manipulation better visible, we also provided a user interface for comparing different figures. You can compare different figures in a side-by-side manner. So on the left side, you have the original figure. On the right side, you have the manipulated figure. But comparing figures in a side-by-side manner is not always very easy. So the changes might be very, very small. So we also provide an overlay. Again, on the left side, you have the original figure. On the right side, the reproduced one. In the middle, you have a slider that you can move from left to right to see the changes. And finally, we also have an overlay. So we basically put the figures on top of each other and compare the two figures pixel-wise. And the changes, this is what you can see in this view. However, the applications also have a number of limitations. Most of the applications provide a link to the reproducible workflow. You can copy the link and paste it into your paper. If they don't provide it, if they don't provide a link, as it is the case with Rihanna, you can still link to a GitHub repository. So it's basically the same procedure. The problem is that some of the applications allow changing or even deleting the materials after you publish them without changing the URL. This means that if you follow the link to the materials, it might happen that these materials are not the ones that created the results in the paper. Remember the two maps in the middle of the presentation that were different. So this could be one reason for that. This means that if you follow the link to the materials, yeah, I already said that. I would assume that a lot of projects are actually work in progress. So this can happen in quite a lot of cases. This can actually be solved with using DOIs. So DOIs are persistent identifiers, and every update generates a new DOI, making it possible to link to the right version of the materials and continuing the work for the next paper. Binder also provides a solution for this problem. So in Binder, you can refer to a specific commit. This is what you can see here. You can refer to a specific commit of the GitHub repository, but still, I'm not sure if many researchers are aware of this option, and it is still possible to delete the entire repository. A further issue is that most journals rely on double-blind review. But the applications do not provide anonymous access to the materials. So if you put a link to the materials into the paper that you would like to submit for peer review, they will find out who you are. Unfortunately, none of the applications has a solution for that. I'm not sure if you have heard of the Open Science Framework already. It's a framework for storing data and any kind of research materials. We didn't include it in our review because Open Science Framework does not consider executable research. It's more about storing. But the Open Science Framework solves this issue of double-blind review by providing or by generating anonymized links. It is a very simple but very effective solution. Finally, none of the applications provide support for sensitive data, which excludes actually quite a lot of research. So this is a problem in research that relies on qualitative data. It's a problem in medicine and so on. I would like to conclude this talk with a few quick recommendations on how to get ready for open reproducible research. And if you are ready for open reproducible research, then you are also ready for the applications I presented in this talk. First of all, start with your own workspace. So I strongly recommend to set up some kind of a hierarchical folder structure and create a folder for the code, a folder for the data, and so on, and also take a second to name files properly. So this can also help already. The second recommendation is learn a scripting language like R or Python. So tools like SPSS and Excel will never be reproducible. I also recommend learning a notebook format. So once you learned a scripting language, this step is rather simple. You should also use a software for versioning like Git. So what I have not mentioned yet is that many of the tools like Binder and CodeOcean rely on repository-like structures. So it might make sense to understand the concepts. But don't worry, start small. It will take some effort at the beginning, but pay off for the rest of your career. And as McKiernan said, she said that openness is not all or nothing. Fully open research is a long-term goal, not a switch we should expect to flip overnight. So that's it about open reproducible research, challenges and opportunities. I thank you a lot for your attention. And now it's time for questions.
Okay, my apologies. So I guess I'm having some technical issues over here. So very sorry for messing up your introduction there, but thank you so much for this talk. I mean, this is great. So many amazing resources that you're able to provide our community with, and we really appreciate it. So, please contact Dr. Kunkel if you need to. Follow him on Twitter. I just have a few questions And just so everyone knows, we will be able to, we will host all these on our website. So, given just, I'm thinking more about this motivation, that you talked about, and I really like, for the researchers themselves, and I really like kind of these selfish reasons that you laid out, because I think that's kind of the way to go when you're introducing this to people. And the big one that stood out to me was being able to rerun the analyses at the time of peer review. I mean, so many times me and my colleagues have, gotten a paper out and felt so good about it, and then it comes back for review and they say, wait, can you run it this way? And we're just like, oh no, now we got to start from scratch. It's been 3 or 4 months since we've even looked at this thing. So, I mean, that alone is super helpful. But I was also thinking, like, how do you motivate researchers to prepare for this ahead of time? Even like at the point of, everything costs money. So like writing this into your grants time, preparing for resources. I know you talked about a lot of these free resources out here, but, maybe just funding for an RA to kind of do all this work for you, at the time of when you're applying for funding, where, you maybe only have $250,000 and you're trying to put it all towards these certain things and trying to figure out, how do you get it towards doing some of this reproducibility stuff. I'm interested to hear your thoughts.
Yeah, I could answer this question in many different ways, so from many different perspectives. So first of all, it's not only about motivating researchers, it's also about preparing them for the future in research, because many funding agencies start requesting for code and data. So they require data and code to be openly available. And I guess this is not the end of the pipeline. So at some point, they will also ask to provide information on the computational environment, for example. Maybe in 5 years or so, they will also ask for using one of these tools to make research reproducible. So it's a bit about getting ready for the future in science. So there is also the strong open science movement that requires more and more, or that's getting more and more popular. Mm-hmm. But it's also about the intrinsic motivation of researchers to make their research understandable. And if you think about these interactive eLife papers, these are only possible if the code is reproducible. But you get the big benefit that you have these interactive papers that support the understanding of the reader. And if your research is understandable, it's reusable, they can build upon the research, they will get more citations, for example. This might also result in collaborations with other researchers who want to continue your research. And then you will also get more papers, maybe.
I mean, that's great. I imagine it's a really good training tool too. If you have somebody that you're mentoring in your lab and just saying, here, reproduce this. If you get the same thing as me, then we're great. If not, then we can figure out where things went wrong, and we can work on that together.
And it's also important to consider that it shouldn't be the case that researchers have to do it by themselves, all that stuff. So they should focus on the research. And it's a bit also the task of universities. I know funding is scarce, but it's also a bit the task of universities to have, for example, data stewards, or maybe research software engineers who can help to make the stuff reproducible.
That's great. I mean, that's such a good suggestion, because we get into our silos and we think we have to do it, or we have to have a research assistant do it, or somebody that's within our silo. But I mean, there's some really smart people, outside of our fields and that know how to do this a lot better than we do. So making those connections, I think, is really key. It's a great point. How about one more question? So, interested to hear about, especially because you've had this experience. I know that, there's some apprehension about sharing data. And I think it came up in the example you gave about the maps, just talking about, how do you navigate these relationships with researchers when you try to replicate their work? You ask them for the data, you replicate the work, and you don't get the same thing that they do. I imagine that there would be, some thoughts from the researcher themselves being like, uh-oh, have they found out that we've done things wrong? Like, now do I need to retract my paper? And so then, in the future, some hesitancy to share data, in the future. So interested to hear just like, what is it like? What has it been like for you? What is it like for researchers? creating these relationships and kind of fostering these and letting people know, like, it's not a big deal, we'll figure out what happened here, but, it doesn't make you a bad researcher because I'm not able to replicate your work.
Yeah, that's certainly true. So it's important to have a bit of this this cultural change that researchers can make mistakes, but of course it's also very easy to say that. So if I think about PhD students, for example, they don't want to make mistakes. And if I tell them, well, it's okay to make mistakes, then they will say, yeah, okay, it's fine that you're saying that, but I still have to get a postdoc position. And if I publish a paper that has errors, then I'm quite in trouble. So this is why it's very important to start with that already from the beginning. So when PhD candidates start at a university, they should get some basic training already at the very beginning to make sure that they consider reproducibility at the very beginning. And this will already prevent many mistakes.
Great. Great. Well, let's wrap it there. We're just at the hour here. So thank you so much. And just, we should have recognized that you are in Germany right now, and it's very late for you. So we really appreciate you coming and talking to us at noon our time in California. We really appreciate it. We hope to stay in touch, and please, come back and visit us at some point again in the future. All right. Thanks, everybody.